Flipped Classroom video for Maths AS Unit 1 Basic Graph Transformations. So we're going to start with translations, and there's the first one we're going to look at I've called the nice one because it works relatively easily. And this is when we have a function y equals f of x. We can easily translate the whole plane in the y direction upwards by adding a constant, or downwards by subtracting a constant. And so what that means is for each x value we first apply the function itself and then we add a, and that just moves the value by a in the y direction. So x goes to f of x, which is the function, and then we add a on, so it just either lifts it if a is positive or moves it downwards if a is negative. As it says, the whole graph then is moved by that value a in the y direction. So we'll have a little look at a video clip now, and we can see that when we're adding 1 to f of x, it moves up by 1. When we add 2, it moves up by 2. So this is why I call this the nice one, because it is pretty straightforward what it does. It just lifts the graph by whatever the value is. And we can have negative lifts, of course. Now, the nasty one. Translating in the x direction is more tricky. For this, we need to add or subtract to the x value and then apply the function. So let's see what happens. Now, in fact, you probably know already from GCSE that when we add a positive number to x and then apply the function, the graph moves in the negative direction. Now, what you may or may not know is why that happens. It may be something you've sort of learnt as a rule, or you may understand why it happens. But let's have a look at why it happens. So, as before, we think about what happens to values. So, this time, because we're first adding the a, then x goes to x plus a, then we apply the function, and this gives us our y value for our original x value. So, we'll have a look at it for a function, and we'll just use a equal to 1, so we're moving it one unit one way or the other. We know in fact which way it's going to go, but let's pretend. And here is our function, and you'll see 2 points marked, one at 1, 0, and the other one at 1.6, roughly minus 1. And what we're going to do, we're going to have a look at what happens to those points. So the point where x is 1, first of all we have to add 1, so going from x to x plus a means going from 1 up to 2. Then we apply the function f of 2. So that is down there. So we've gone for the x value has gone from 1 up to 2. Then we've moved on to the function. But that value is, for the new situation, the f of x plus a, that's going to be the y value attached to 1. So the point that all that gives us, and I indicate that by sort of dragging it backwards 1, we end up with the point 1 minus 1. Okay, the other point we were going to look at was when x is 1.6, so we'll start there. And when we add 1 to 1.6, obviously we get 2.6, so that takes us across that way. We then move on to the function itself by going up to it. So we're now at f of 2.6, and that is 0.9. But this is the y value for the original x value of 1.6. So we have to take that back again, and we get the point 1.6 comma 0.9. So we'll mark that on. And now you can see why the points are moving backwards, even though we're adding 1 to the original x's. Because we go forward and fetch the value from the curve and then take it back again, then the whole curve moves back by 1, in this case because a is 1. And so f of x plus 1 is f of x translated 1 to the left or in the negative direction. So in other words, translated minus 1 in the x direction. Okay, there is another way to look at this, and that is to describe the translation and see what that means in terms of the functions. And that sounds a little bit gobbledygooky, but let's do it and then you'll probably see what I mean. So we think about translating a function f of x by a in the x direction. So we'll draw a picture of it. So the green function has been translated, moved up 1 in the x direction. By a, sorry, not by 1. So each point, xy, has been translated to x plus a, comma y. Well, that makes sense. We're translating the whole thing by a, so we're translating each point by a. And if we call these new points capital X, capital Y, then we know that capital X is equal to little x plus a, and capital Y is equal to little y, because they are the same points as the translated ones on the line at the top of this column. Okay, now that means that little x is big X minus a, and little y is equal to big Y. And if we put those values into our function y equals f of x, we get big Y equals f of big X minus a. Now, the y and the x can be replaced by little y and little x because they're arbitrary, so the relationship's the same whatever letters we use, and that tells us that the blue curve is indeed y equals f of x minus a. So even though we were adding 1 onto the x's, we get the graph transformation is f of x minus a, which again, you know this, but this is just looking at different ways of getting to grips with y. It sort of could be seen to be counterintuitive. Now, another way to think of it is that because the translation is acting on the x value before the function is applied, if we think of it as moving the x-axis, so if we imagine the original axis is the dotted line, and the original function is where the blue one is now, we could think of the x minus a as moving the axis by minus a. So subtracting a from x moves the axis in the negative direction and leaving the function where it is, which has the same effect as moving the function in the positive direction. So we can think of the graph transformation as transforming the axes, and then there is a consequent change to the function, or the relationship of the function with the axes. It's all quite difficult, lots of practice, and it'll make more sense. Okay, stretching. Nice when we stretch in the y direction. So if we multiply the function by a number a greater than 1, the function will be stretched away from the x-axis. And if we multiply by a less than 1, it will be compressed towards the x-axis. So for each x value, we first apply the function and then we multiply by a. So we have x goes to f of x, and that then goes to a times f of x. And that will be our new y coordinate. And for a greater than 1, that means that the whole graph is going to be stretched by that multiple of a. And we can have a look at a few of them. Here we've got y equals f of x. And if we have 2f of x, it's been stretched double the height, triple the height for those the maximum, and triple the depth for the minimum for that matter, and then times 4. So the whole thing's being stretched away from the axis. And if we have a less than 1, this means the whole graph is compressed by a factor of a in the y direction. So we start off with y equals f of x, and if we have y equals a half f of x, that means f of x divided by 2, so all the points are half the height and half the depth for that matter, because we're interested in the relationship with the x-axis, or the y equals 0 line. And same with a third, means it's a third as high, and a quarter similarly. So that's compressing the whole function towards the y equals 0 line. Now, again, in the x direction is going to be more tricky, so I've called it nasty. It's not really nasty. Really nasty is poking people in the eye, but it's sort of mathematically tricky at least. And for this, we need to multiply or divide the x value and then apply the function. And as before, you probably know, or you might know from GCSE, that when we multiply x by a number greater than 1 and then apply the function, the graph squeezes rather than stretches, which is sort of the opposite to what happened when we were doing it in the y direction. So the reason is a similar sort of idea to what we had before. Because we're multiplying by a and then applying the function, then we are getting values from elsewhere and bringing them back again. So let's have a look at this for a function with a equal to 2. So we've got a couple of points marked on. The first point, that higher up one there, is at about 0.3. So when we double it, remember we're timesing by 2, a times x, or 2 times x in this case, that takes us to 0.6. We then find out what the value on the curve is, so a bit above 0.4, and we take that value back to our 0.3, our x equals 0.3. Okay, now for the point just above 0.8, when we double that, that takes us a bit above 1.6. We then drop down onto the curve to get our y value, and we take that back to where we started, just above 0.8. And we then mark that point on. And you can see that that's going to happen for all the points. They're all going to be squeezed in by a half or divided by 2, whichever way you want to look at it. And so f of 2x is f of x squeezed by a factor of 2, or you can think of it as stretched by a factor of a half. So be a little bit careful with the words stretched and squeezed. And then, as we can see, the whole function is being squeezed in by a factor of 2, or stretched by a factor of a half. We can look at this as well in terms of the functions in a similar way as we did before. So if we stretch f of x by a factor a in the x direction, so this time the blue function has been stretched to give the green one by multiplying by some factor of a. Each point xy has been stretched to axy, so we call these big X and big Y. So we have big X is ax, a little x I should say, and big Y is equal to little y. That means that little x is 1 over a times big X, and little y is big Y. And we can substitute them into the y equals f of x. That gives us y equals f of 1 over a times big X, and because the relationship is the same, whatever letters we use, that becomes little y equals f of 1 over a times little x for our new curve. So we can see that a stretch by a factor of a actually gives us, in terms of a function, that will give us the function 1 over a times x. Flipping graphs, eh? Well, scaling by a negative. What happens if a is less than 0? And what happens is that the scaling happens as before, but in addition the graph reflects. So it reflects in the y-axis, or the x equals 0 line for f of ax when a is less than 0, and in the x-axis, or y equals 0 for a of fx if a again is less than 0. We're mainly interested in the case a equals minus 1, so this is when we're looking at f of minus x or minus f of x. So for f of minus x, we can think of the multiplication reflecting the whole plane in the y-axis and then applying the function. So that looks like that, which is slightly strange to look at, but essentially doesn't matter which one we think of as the function, in fact, because they've just been reflected in the y-axis, and so the green has reflected to the blue and vice versa. For minus f of x, we can think of applying the function and then reflecting it, in which case we're going to reflect the whole plane in the x-axis, or the y equals 0 line, and that means we get that situation where they've been reflected vertically, if you like.